behalf of Rise Energy, we're a startup company out of Ames, Iowa. We'll be focusing on autothermal pyrolysis for production of biochar, but also biocrude. We got some questions about basically what is bio-oil, right? Wood vinegar. So here's another new term, largely similar things, but biocrude is going to be the focus of my talk today. So kind of the opportunities that exist for us as a company is there's a diminishing space for underutilized waste. We've had a lot of customer discovery and discussions with potential partners that have really millions of tons of aggregates that they have to pay tipping fees for and need something to do with that type of feedstock, and that's where our technology comes in. There's regulatory pressure to hit renewable volume obligations on fuels, destruction of PFAS and other feedstocks like that. And then there's just an unmet demand for renewable carbon sources. There's talks going on right now about graphene in the steel industry, et cetera, as well as that unmet demand for that carbon sequestration, which a lot of the biochar is focused on. At Rise Energy, we're really focused on becoming exceptional stewards of those resources, where we take the feedstock, the aggregate, the biomass, we convert that into those intermediate products that then can be used as building blocks for higher value eventual end use products, whether that's on fuels or chemicals, et cetera. This is Ryan Smith. I'm our CTO. We got Jordan Funkhauser and Steve Smith back here, also part of Rise Energy. So hopefully we'll be seeing you around the rest of today. We're coming out of the university to a startup, and I want to add a disclaimer to that. It's not typical university startup. We've got, between the three of us, over a combined 40 plus years of experience, not just in thermochemical, but highly in this field, pyrolysis, and on the commercialization aspect. So as we just heard from our first speaker, right, there's a lot of lessons learned as a startup company there with Charm. Luckily for us, federal agencies paid that learning through grants, right? And so for the past 2 decades, we've kind of learned those, and now we really have the commercialization. We're ready to commercialize the technology, and that's exactly what Iowa State University is doing. And so we have licensed all of the technology I'm going to be talking about today from Iowa State. Here's a picture of our actual pilot scale plant right there. It's about a 0.5 ton per day system, and we'll get into that coming up. Oh yeah, so from the technology aspect of it, Rise Energy really focuses on 4 main things. The first one, the 2 aspects of our core, the first one is our autothermal technology. The second one is the fractional condensation, fractional recovery we heard about. This gives us a high quality product that then we can then have different upgrading routes to really maximize the value from it. And then the fourth aspect is how do we harness the economies of it with the modularity. So let's dive into that first one, the autothermal pyrolysis, which is really the heart and soul of Rise Energy. It's the core of our technology. A lot of talks today. This is the first time I've heard the word bio-oil today in the first presentation, so luckily we got a good background on it. But it's really been focused on maximizing that biochar production, which is via your slow pyrolysis technologies, right? You can get yields up to 50% of biochar with technologies like kilns, auger reactors, other various slow pyrolysis techniques. And typically this is done via conventional pyrolysis, so in an inert atmosphere, which requires you got to have nitrogen purging through your system at all times to prevent any burning up of that biochar. And then on the flip side, if you're trying to maximize for oil production, that's where you get fast pyrolysis, which we heard from the first talk, where you're really trying to maximize that bio-oil recovery, which can be anywhere between 50 to 70% of your biomass, and when you collect all of your liquid, that overall bio-oil. Because of this, you reduce your biochar yields down anywhere to 10 to 25%. Again, very stringent on your typical feedstock. Now, with conventional pyrolysis and fast pyrolysis, there's limitations that prevent really the cost-effective scale-up from this. The energy required to pyrolyze, or also known as the enthalpy 4 pyrolysis, will range anywhere between roughly 1 to 2 megajoules per kilogram of your feedstock. That's roughly 10% of the overall energy content of the biomass or the feedstock itself. So you have to provide this energy just to get to the pyrolysis technology going. So as you scale these types of reactors, they become very heat transfer limited, which ultimately causes a major issue with the cost. And you can see there, because of the heat transfer, as you scale, it actually scales linearly. but you get really high costs just because you're restricted on getting the heat and getting that energy for pyrolysis. Conversely, if you can scale due to just chemical reaction limitations, that scales at a factor of about 2/3. So a factor there about 2/3. So it scales lower, allows you to have a lower reactor and then thus capital cost for your overall plant. So our technology, this autothermal pyrolysis, comes in and really allows us to overcome some of these barriers. So what we do is we take biomass and we do not shy away from the term air or oxygen into our system. That's really the core of it, right? That's kind of taboo in the pyrolysis field. But what we really want to do is we want to consume some of that biomass internally to provide the energy needed to hit the pyrolysis reactions and overall yields. And so by doing that, we introduce air through our system, and this operates at around equivalence ratios of around 10%. Gasification technologies, roughly 20 to 40% equivalence ratios, and then we just talked about combustion, you're at the 100% over if you're in terms of excess air. So we're really limiting the oxygen, but we're using it as a catalyst or a tool for our technology to become very energy efficient. Not only do we do this, we are not consuming desirable products. We still maintain the overall fast pyrolysis yields. In fact, you can't get truer of a definition for fast pyrolysis than through autothermal technology because of our introduction of air and the consumption, we are having internal heat transfer. So we remove that heat transfer, but you're also got the fastest heating rates possible to get you the highest quality bio oil. This autothermal pyrolysis, as I said, removes those heat transfer limitations. So as you can see here on the left-hand side, this is actually a plot of conventional versus autothermal pyrolysis for throughput of a reactor versus diameter. So as you increase the diameter of your reactor, in this case we're talking about a fluidized bed reactor, you're very limited by throughput due to those heat transfer limitations. You simply cannot get the heat to the actual biomass to hit the reactions that you desire. By utilizing autothermal, you actually scale with the square of the diameter, so you get a much higher throughput in the exact same system by utilizing air and removing those heat transfer limitation. This allows for a process intensification, which is what you can see there on the right. These are two different flows. The top one there is nitrogen pyrolysis or conventional pyrolysis. So on our pilot state, a pilot reactor at Iowa State, putting red oak through that system, you're able to put about 4.5 kilograms per hour through that system. By transitioning your gas media to use oxygen and air, we eliminate the heat transfer in the exact same reactor. We actually put 3 to 5 times as much throughput in through the system, while you can still see maintaining the overall rough percentages of product yields. So this autothermal really unlocks very huge commercial benefits. First, it lowers the, there's supposed to be 1, 2, and 3 there. So the first one is it lowers the capital costs by 25%. So because of conventional pyrolysis, where you're stringent or you're required just to have only a nitrogen atmosphere, you need capital that's associated with that, whether liquid nitrogen tanks, et cetera, so that you have media there. All we need is an air compressor to get air to our system. We remove high capital intensive stuff on the front end, which overall reduces the capital cost. Because of that process intensification, we're able to build smaller while still harnessing more feedstock in the local aggregates. And then the third aspect is it eliminates the need for fossil energy. So a lot of companies use obviously natural gas to provide heat, use external heating to get that energy required for pyrolysis. Because of our autothermal technology, we're generating that ourselves. This allows us to reduce the carbon intensity of our overall process. We're strictly just burning biogenic carbon, so there's not an increase in net emissions from that aspect. Now, I mentioned the Iowa State Pyrolyzer. That's something that we've been working on for the past 10, 15 years. That's at 0.5 tons per day at Iowa State University. Jordan's also here on behalf of Iowa State University. Iowa State partnered with Harry Stein from Stein Seed and actually built the first commercial autothermal pyrolyzer, which is operating at 50 tons per day. It's operated at capacity continuously using agricultural residues. Corn stover has been the main feedstock of purpose for this particular system. You'll see there it's on the right. It's kind of set up in the modular grids, which I'll get to in a little bit. At the lunch keynote we heard yesterday, there's a lot of Iowa representatives that toured some facilities and became big proponents of biochar and the pathway for it in our economy. Well, spoiler alert, there's a picture of the actual system that did the convincing. So the autothermal, short summary to all of that is the autothermal process has been proven already at the commercial scale. Rise Energy is looking to actually take that to the next step. We also heard on the first talk this morning about fractional recovery. So how can we really get the optimal value of that bio liquid, that bio oil? So Iowa State developed and patented the fractionation technology that we alluded to, where it used a series of quenches, condensers, electrostatic precipitators to try to capture all of your potential bio oil. And typically what the big proponent of this is you're able to separate it in different desired cuts. So kind of like a reverse distillation process. And we talked about wood vinegar, the pyroligneous acid. That's very light compounds of the bio oil, often mixed with a high concentration of water. That's actually there represented would be in the blue schematic, so lower temperatures to collect them at. Rise Energy is really more focused on the heavy biocrude, which I'll get into a little bit. That's the real viscous material, the very energy dense material. And so by separating out through this fractionation, you can selectively choose what compounds you want to condense out of your vapor stream. By doing that heavy crude, you're able to get a moisture content less than 10%, i.e. really eliminate some of that oxygen, which is undesirable for potential upgrading opportunities. So we ran some pine on our system, dry pine. The picture on the left is our actual heavy biocrude cut from that first half, and that yields at about 30 weight% of your feedstock that goes through. So roughly a third of your feedstock, you can really get into this high quality biocrude, which is less than 10% moisture content, very high in carbon content. You can see roughly 60 weight%. Now, because we're at a biochar conference, I have to have some due diligence and do a biochar slide. So you get a half of a slide right there, focused on the biochar. Out of this process, we still yield about 15 weight% biochar, but it's very high quality biochar in the aspect that it's 70 weight% fixed carbon. It's roughly 80% carbon content itself, and then hydrogen content's 3.5 from that aspect. Iowa State's done some studies on the recalcitrance of this, so the non-label portion of that biochar, and from everything that we've seen, our biochar that comes out of autothermal pyrolysis is roughly 90% recalcitrant, so not going to biologically or microbially degrade along with the thermal degradation. So a very high quality biocrude. That's really our focus from the fractionation technology. So now the question is, what is it that we can do with this biocrude, right? We heard from the first talk here, you could pump it down in oil injection wells. You could burn it for CO2 sequestration. We look at it as there's potential many more opportunities. And I want to highlight, we call it a biocrude because we truly see it as a crude substitute to petroleum. It's very viscous. It looks like crude petroleum. Downsides, it's got a little bit of oxygen, so you got some unbad characteristic reactors that we heard of that you got to handle. One of the ways Rise Energy is handling this is actually a stabilization process, where we take that raw biocrude, that heavy cut, we introduce that with hydrogen in the presence of a solvent and catalyst, and we actually, at low temperatures and low pressure, we call this hydrogenation, we convert some of those kind of bad unstabilized actors into a stabilized portion. So we convert carbonyl groups to alcohols, saturated vinyl groups to aliphatic groups. And what this really does is it drives down and dramatically reduces the viscosity of that oil. So that picture that I showed and was holding, viscous at room temperature. I can put it upside down, it's not going to drip down. Take that same cut, do this low pressure, low temperature stabilization process, it becomes non-viscous. It acts less viscosity than actual maple syrup at room temperature and even refrigerated. So it flows. I got a jar of that on my desk. It's stabilized, so it's not going to oligomerize over time, which is very common in the pyrolysis and one big barrier in the commercial applications. So our stabilization removes that aspect of it. This allows us to transport it efficiently, effectively, and maintain its high quality to future upgrading technologies. Another aspect, depending on what feedstock you're putting into the system, if you have a feedstock that's high in cellulose content, high in potential sugars, glucose, xylose types fractions, there's a potential interest to extract the sugar fraction out of your bio-oil. So we have a liquid-liquid extraction technique where you actually take the biocrude, that heavy stuff that comes out of the system, mix that with water, and you'll get a water-soluble content, which your sugars are retained in there. You can see on the right a picture of pyrolytic sugar syrup. And then you get a phenolic-rich fraction, which has a lot of the phenolic oligomer stuff that's coming out of the lignin portion of the feedstock. So through this separation, you're able to get two different kind of product pathways. From the sugar portion, Iowa State's done a lot of looking at making purified sugars out of this. So you can take that pyrolytic syrup, go across industry-based resin technologies to produce high-quality sugars, crystalline-based sugars. A couple years back, we did a TEA out of Iowa State where you produce pure levoglucosan, and just the economies to break even on the overall pyrolysis process, you could produce levoglucosan at over $1,000 per metric ton, and that is over 1/10 of the current selling price of levoglucosan. So the point there is you're able to produce high quality potential chemicals and other compounds coming out of the sugar fraction. There's a lot of interest in sugars for upgrading to alcohol to jet, right? So depending on your feedstock again, you're able to get potentially 20% of your overall feedstock coming in could come out of this sugar fraction. And then the other question is, what do you do with that phenolic-rich fraction? Or if there's not a lot of sugars in there, just truly the original biocrude. And so Rise Energy sees the long-term pathway to that, not tomorrow, but the long-term pathway is actually the production of renewable fuels. So Iowa State partnered with Pacific Northwest National Laboratory and successfully hydrotreated this biocrude fraction, this phenolic-rich viscous biocrude, into renewable fuels. So fuels that are indistinguishable from petroleum in terms you can set them side by side. Approximately 40 to 50% of the fuels were in the gasoline range, while another 45% was in the diesel range. And so about a barrel of that biocrude that can come in can produce about a barrel roughly of actual fuels coming out of that. Iowa State is still very much interested in this pathway, obviously. We're currently working on a USDA grant with a top 5 petroleum refiner to actually upgrade this through a pilot hydrotreating system that's representative of one of their biorefineries. And at Rise Energy, we estimate there's a potential of approximately 150 liters of fuel per ton of feedstock. This is important because I mentioned there's an unmet demand for some renewable fuel volume obligations. This pathway would give you access to unlock some of the D3 and D7 RINs that are not currently being locked out there, so get high value for that biocrude. Now, another option for the biocrude is actually to use that and go into a bioasphalt. This is something that Iowa State worked on with a lab there. We're producing performance-grade bioasphalt, where you take that phenolic-rich portion and you actually blend it with ground tire rubber. And we achieved a performance-grade asphalt of 58-28. 58 represents the temperature in Celsius at the higher limit that asphalt can be at, so 58 C, and the lower is negative 28 degrees C. This was actually paved, a bike path in Des Moines, Iowa. The Waveland Bike Trail was actually paved with this bioasphalt produced out of the pilot scale reactor from Iowa State University. So it's been very successful so far, still investigating potential partners and future opportunities with this bioasphalt, mainly because it's a promising and less hazardous substitute to bitumen. The last aspect I want to talk about here is the modularity that we're focusing on. We believe in being able to harness economies of mass production as opposed to economies of scale. Economies of scale means as you build bigger, you actually decrease the overall capital costs from that perspective. However, because you're building very few of them, capital projects are very, very intensive, so harnessing the actual cost savings takes a long time. But building modularity, you can actually harness the Wright's airplane model, where you learn more by producing more of the exact same equipment, right? So a learning rate of 20%, which is industry standard, means for every doubling of throughput capacity, you actually reduce your capital costs by 20%. And so roughly in some of our calculations, by the time you hit the 20th or 30th system, you hit your what was typically called the nth cost from your capital aspect. So this really allows you to save on capital intensive projects. And because of Rise Energy's autothermal technology, you're able to get a lot of throughput from a very tiny reactor. We're able to build modular, right? So the picture I showed earlier of the Stein system, it's a 50 ton per day plant, but it's built in modular components. So you're putting them together like a Lego brick. This is not to be confused with mobile, as we heard in the first talk. This is just production modular, so it's mass produced at an EPC and construction firm, and then shipped to wherever your plant would be. So this has been successfully demonstrated at that 50 tons per day scale. So all of that has been combined through Iowa State University published a techno-economic analysis at what is believed to be the kind of the sweet spot for this kind of technology at 250 tons per day. So some of the assumptions that went into this TEA analysis is basically not only from harnessing the sugar fraction, but getting a value of about $500 per metric ton of phenolic-rich biocrude. And then the assumptions in this was an $80 per metric ton of biochar, which I think know at this conference is relatively low on the biochar, so that allows you to lower kind of your value for the biocrude. We think the biochar can be anywhere over $300 per metric ton, depending on your potential applications. So Rise Energy, our internal analysis suggests you can be profitable at the smaller scales in the current carbon markets than this 250 tons per day. So transitioning Rise Energy, we're poised to really become the industry leader in the domestic production of this biocrude, and specifically the stabilized biocrude. Our long-term vision is to have dedicated lines to a biorefinery. We recognize that's not happening tomorrow. Industry's not ready for it. We're able to produce biocrude that's able to be ready for it, but the industry's not there. So we're harnessing some of those other opportunities, discovering aspects like the bioasphalt. The stabilized biocrude can also be used as a marine sulfur fuel for a shipping potential generator. So really using short-term on the energy resilience side, and then also capturing value on the biochar. We see kind of optimal commercial ranges anywhere between 50 to 300 tons per day of feedstock input for a Rise Energy plant. So I mentioned we were started up out of Iowa State University. We actually were founded in 2022. We've gone through various accelerators out of MIT and in Iowa. In the early conception, our research group, Dr. Brown's research group, the Bioeconomy Institute at Iowa State University, was actually one of the top 12 milestone winners for the X Prize. So the group was one of the 12 out of the 1,200 applicants that initially Rise Energy wasn't formed at that time. We came in later and partnered with Harry Stein, the Stein system, and Iowa State University, and we're therefore officially a top 100 finalist in the X Prize for carbon removal. Been working with strategic potential partners, doing feasibility studies, aspects like that, while still at the university, and right now we're targeting to officially jump off from the university, get those handcuffs off, if you will, and really get our first commercial system built and in the ground and up and operational by 2027. So really purpose of being at this conference, first public introduction to Rise Energy, but evaluating strategic partnerships, able to license our technology, so happy to talk about that. We're also in the fundraising aspect to get this commercial plant, so be looking forward to that and learning more about securing carbon credits and from the carbon market from that aspect. So with that, I'd like to thank you and then field any questions.